My brother's oh shit, yeah. That is. That's why I committed all the yeah, it's related to our thing. Still we gotta be able to would agree, yeah. Like if you see
All right, everyone. Okay. Well, welcome to the class after the last exam. And obviously, any of the lecture content from now on will not be on your exam, but still some good content to know about for the sake of learning embedded system in this class, and probably for some of you, the final projects as well. All right, let's get the lecture started. If you haven't found a seat, please try to find a seat. There are a lot of empty seats in the front, so don't have to squeeze all in the back. Today, we're going to talk a bit about PCB design and a few other things, if we have time to get to it. Basically, how to make circuitries and stuff from breadboarding to either PCB or other form factors, basically. Before that, some announcement. The most anticipated will be the exam 2. So we haven't finished grading it. It's 91% done, and we are going to finish it tonight, hopefully, and then we will post the grade after with the solution so that you guys have all the weapons you need to argue with us. So far, this is what the distribution look like. Do not get scared by the scores. They are 18. They are 18 points haven't been graded. So it's not finished yet. But just give you a perspective of how the grade looks like. Yeah, it's not like no one gets above 80. That's impossible. So there are still 18 points of the class not being graded. But this is the so far the distribution looks like. Yeah, I don't know. It looks pretty nice. What do you guys think? Say if everyone magically got 18 points, we will have a mean of 80, which obviously not going to happen. But anyway. Okay, I will let you guys talk for 30 seconds. But yeah, we will release the grade either tonight or tomorrow before my office hour. So, All good? Everyone finished complaining about it? Okay, cool. So on this Thursday, the lecture will be doing a special topics on the health sensing in embedded system from a HCI perspective. It's a lot of it. It's kind of from my own research, and I think a lot of them have a good amount of overlapping with the embedded systems because a lot of those devices or methods are building either with embedded system directly or with a similar mindset of all the method design principles with a general embedded systems. So I will give a lecture on that. So give you a little bit perspective from HCI or human-centered or human-computer interaction. Basically, by that definition, the health sensing devices we talked about, or health sensing in general, in that lecture, it's going to be mainly from human or user or patient, however you want to call it, their perspective, rather than from doctor or clinician's perspective. Not that they're not human, but they're super professionals. They interact with those big, chunky equipments that are going to go through much different design principles because of all the FDA approvals on these high power machines. For us, it's usually portable devices, portable systems, or low power systems. Low power meaning probably the most common ones 3.3 or 5 volts, or your phone is still also considered low power. But for say MRI or CTs, those big equipment would be usually considered as high power because of the amount of current needed to generate those magnetic fields. Okay, and we're gonna have the student presentation, the team presentation, starting next Tuesday. So the topics and the date assignment is posted on the website, also on the Piazza. So do check it out. If you have any conflicts, let us know as soon as possible. We do rank the slots based on the topics, so that the topics that are going to be most related to what most of the class is going to be using for their final projects is going to be listed up front. Of those peripherals or devices that's a little bit less widely used are going to be put a little bit like later date. So we will try our best to keep the schedule like that. But if you do have some like absolute conflicts, let us know, and it'll be much easier if you kind of already find someone who could swap with you, and then rather than we sit down and find someone to swap together if you do have a team conflict. And for those presentations, attendance is required. Obviously, for the presenting team, you have to be here. Otherwise, yeah, I don't know what else you're going to do. And for those who are here, we're going to talk a little bit more on this. But basically, we're going to have like a peer reviewing process of the presentation. That's going to count about like 25% of their presentation grade. And that's going to count towards your participation as well. We anticipated to have 6 to 7 lectures to cover all the teams we have, because we do have a rather large amount of people this semester. So you are allowed to absent from 2 of them. So it's okay that you miss 2 of them and then attend the rest. You will still get the full participation credits for that. Yeah, and a little bit more on the presentation. Starting next Tuesday, currently, ends about April 15th, but we might have a little bit wiggling in case you guys need more time for your final projects, or if there is some other interesting topics you guys are interested in, and we think it would be good to include it inside of the lecture. We will be having 4 teams per lecture, each team having total 15 minutes, 12 minutes for the presentation, and 3 minutes for the Q&A. So it's going to be like, I think hopefully the schedule will work out, plus 2 to 3 minutes, maybe 2 minutes for swapping teams, etc. So that should give us a pretty full lecture time. And you're required to meet with the teaching team, which is us, at least 1 day before the presentation. We'll put these signing up slots online later. It's usually going to be the day before your presentation, so that each of you have like 30-minute slots, and then this will be used for basically evaluating whatever you have prepared so far and any of the questions like we have for you, so that helps you better prepare, or you have for us, which part of the content to cover more or cover less, etc. Oh, any questions on this so far? On the student, like the team presentation? Let me a little bit more. So in total, this will be 6% of your final grades. Generally, everyone on the same team should get the same amount of grades. We might have like 1 or 2 people have to do it remotely. I think we'll find out a way together. I wouldn't be too worried about that. So it can be done either through like a recording, or maybe we put your face on the big screen for 5 minutes. The whole grades of this is split into like 25% preliminary plus 75% in class. The 25% preliminary basically is the amount you spend with us before the class. So, do come prepared a little bit. Don't come in with, no slides or 100 slides, and then in order to go through the whole thing together. That's not going to be fitting in a 30-minute slot. So be reasonably prepared. We're not going to grade you too harsh on that. So as long as you put in reasonable amount of work, and then the content is like well thought and covers sufficient enough content of that topic, then you should totally be fine. And the 75% in class is going to be 50% from us again, and then 25% from the peer review, which is the Google form that you guys are going to be filled out during the class, during the lecture. We don't we don't rank anyone, so just pretty much purely based on that performance of that team during during the presentation. Just be honest, and then how much you learned, and what's your thoughts on potential improvement, how well their Q&A sessions, etc. So for that peer-reviewed part, which is basically for the rest of class, the Google form will be posted, and at least attend. If we do end up have 7 lectures, at least attend 5 of them. If we have like 6, attend at least 4 of them to get the full participation credits for this part. Okay, everyone's good? No questions? All right. Some strategies, in total, because in total like 12 minutes of presentation time, probably you prepare like 10 to 20 slides, depends on how many content you put on the slides, also how fast you guys speak. It's kind of like a personal preference. You might heard people said that you should spend at least 1 minute on every slide. That may or might not be true. That usually holds for those like super senior folks who can talk about their lives for like 30 minutes without any slides. They're totally able to do like 2 to 3 minutes per slide even. But for like a more introductory, you might want to have some of the slides go a little bit faster and some of them go slower. So, but totally up to your own presentation skills. And some of the structures to consider, these are just big words. You could break them up into, what, why, how, what basically introduction of this topics, what it is, how it works underneath, and why this thing exists. What's it good for, and what are the gaps it fills. Like without this, we're not able to do this. Or for example, I don't know. If you do like geophone, no one is doing geophone, but we use this so that we can get like lower frequency vibrations compared to say IMU, etc. And how is basically how you communicate, or how to use it, right? You use this through. You are able to use this through, for example, I2C protocols for a lot of these sensors, or you're able to use it with maybe the STM we have, or some other microcontrollers or computers. Basically how to use it, and maybe if you have time, put some limitations. Within this type of like, what's the limitation of the topic or like the device you're presenting, right? What is it good for? What are the edge cases it might not work? What's the range of usually how this type of sensing mechanism covers, etc. For example, if you do like step motor versus servos, like what are the trade-offs or cases that maybe better use this versus better use that. And of course, trying to stay engaged. Obviously, this is my first time teaching this class, so a lot of my engagement can also be improved. But I guess, do what I say, not what I do. Try to stay engaged for the class, for your presentation. Any questions? This is the last slide for the student presentation. So if you have any questions, now is the moment. Or not? Okay, let's go to, okay, yes.
So the surveys after each student presentation, does everyone have to complete those as part of the participation?
Yes, as the audience, you have to submit your answer by the end of the class for the participation score, yes. The question was for, do you have to submit the Google form in class? All right, cool. So today we're going to talk a little bit about the PCB design, which can be relevant for some of the teams, but it might be a little bit stretching. But I think it's a good thing to mention and talk about, because that's essentially a lot of if you have like an end product, or you want to have like a high fidelity prototypes in the end, this is usually what you're going to have to go through in the end. Before we go to the deep of that, let's first take a quick look at how people do like early stage circuit prototyping nowadays. So basically, no surprisingly, breadboard. You guys are hopefully all familiar with this by now. They are easily plugged and unplugged, basically corresponding to like reconfiguration, very easy to reconfigure whatever you have in your circuit, right? It's also easy to reposition your components. It gives you like high reusabilities because all the components on board, you can just take it out and use it for other prototype or other circuits, as well as function flexibilities. Always feel free to add another sensor modules for your I2C as long as they have different addresses. You don't have to, and you can change the code much easier as well. Which pings everything connected to, so to speak. And on top of that, it have a bunch of available, out-of-shelf sensor modules for you to use on the breadboard. This whole package, basically called like during line package. It's essentially whatever like the ping space is, I think 2.54 millimeter. Yes, and then that's just compatible with the standard breadboard design. So yeah, pretty neat especially for like early stage prototyping. However, when these breadboard with the circuit on them being testing onto a later stage, for example, when you're trying to move on to like a physical prototype or physical like a product, they don't really fit very well with the physical form. Yeah, pretty straightforward. It have like very low form flexibility, so to speak. So what do we do about that, right? So what people usually do is they build like a customized PCB board, printed circuit board. It's a heart shape for no particular reason, but it's just a very weird shape, so that gives you an idea of which type of it's quite freeform to a certain extent. It's very hard to do like 3D shapes, etc., or like doubly curved nowadays. But on like a 2D or 2.5D-ish, we have a lot of flexible on how these PCBs can fit. And obviously, they fit to the physical objects very well, but they also have the downside. As we remember in this course, over and over again, there's always some trade-off point you have to make when you decide which way to go. And I guess for this one particularly, it's the trade-off point for you, for your final project, to decide when to, if you do want to do the PCB manufacturing, when to place the order. Basically, the downside of this is it's very hard, not impossible, but like very, very hard to move components, especially if you already have the wire underneath. So you can change components, but you can't move the traces underneath with it, right? Also, even if you're swapping or changing components, it requires additional like soldering and desoldering. The whole manufacturing, like the turnaround time, as they call it in the industry, it's going to be much larger than this as compared to breadboard, just plug and unplug. Here, it requires usually at least a week, sometimes more than that, 2 weeks for the whole turnaround time, plus the assembly time, etc. There are some like in-betweens, which they call like protoboard. Not sure how many of you guys work with this. It's pretty much like a, what is it like? It's kind of like a breadboard, but like thinner and doesn't have all those interlinked channels underneath. Each of these holes are pretty much standalone. So you will have to solder any of the components you want and then make like physical wires on top of it in order for it to connect. Or yeah, I should probably include like a backside of this image. A lot of the wires was connected on the back. So for this one, it's kind of in between, right? It's still very hard for you to do like design iterations on this, but it does give you some of the good part of the breadboard, which is most of these components, like the during line package, are still compatible with the protoboard. But you do have like limited form factors you have, etc. But this one is much more rigid than the breadboard. If you think about it, if you have like a moving little tank thing, breadboard, if you directly put a breadboard on it, if it hits something, some components might fall off and doesn't work. For the protoboards, usually it holds pretty well because you soldered on it. It's almost as good as a PCB board, so to speak. So if you do want to have something moving around or some like last minute fix, if you don't have time for the PCB ordering, this is one of the good alternatives to consider. All good? Okay. So now that just assume you want to make a PCB, like a printed circuit board, how does it work? right? So basically, at the end of the day, it's a set of wires plus all the components connected together. There are some more design considerations compared to the almost like free to play around, like a playground as a breadboard. It has the recommendations on the dimensions of the wires you use. Usually you use standard sized, but some components does require you to have specific, maybe gaps or the width of the wires in order for the components to working properly. And those wires are very thin, so that they end up being like high resistances or like high reactance if you have like AC signals. And then sometimes that also results in the crosstalks. So the wiring or the routing options here become like more critical if you're working with high frequency signals or work with very high power components. And like we said before, you can't change easily once you have built it. This is like I think one of the more special case of the PCB board. Usually you don't see these type of big components on it, but this is also possible. So if you do want to use the During Line package that was built for the breadboard or proto board, you can also still do that on the PCB board. Just make sure you have the footprint corrected for them. But usually, they use something smaller. For example, on the right, those type of package, SMD, surface mount components, basically. Yeah, so some basic terminologies in the PCB design. We have traces, which is the wires that you're lay out and then trying to figure out where to go and what to connect. We have layers, which is different layers of your board. If you do like breadboard, you can consider them as almost like I guess 1 layer or 1.5 layers, because some of the wires could go on top of each other. But with PCBs, it's very, very, I think mostly the most minimum amount you will see is probably 2 layers, because it doesn't cost any extra money to just use the top and bottom. A lot of them have like 4 layers, pretty typical, or more than that, 6 layers, etc. 4 layers are pretty typical for a lot of the microcontrollers you work with, like the microcontroller breakout board, because inside you have like 1 layer of grounding plate, and 1 layer of say power, or you have 2 grounds, analog ground or digital ground. Different ways to configure it, but usually with the PCBs you have multiple layers. And the through holes, basically the hole for the pin components to push through the soldering down. For example, if you have those type of components, sometimes they require to go through the thing. It's less common in more complicated designs, but for like 2 layers or some like very, very large capacitors, they do still require these type of through holes. A via hole, it's basically a hole that connects the different layers. If you think about it, what's a good analogy? So the via hole usually goes through the whole thing, but depends on whether you have the wire or a connecting point around that location that goes through. It decided whether that layer or that trace on that layer was connected with whatever on the top or on the bottom. It doesn't necessarily connect the top to bottom. It could be connecting the inner layers as well. Usually the via holes are through holes, although not all the layers are necessarily connected. Those holes are also usually very small in size. So yeah, typically they're also covered with like masks. So you wouldn't necessarily see them, but aware that they're there. And we also have the surface mount, which is the one I mentioned, the SMD components, the surface mount devices that usually are like IC chips or passive components, resistors, capacitors at various different sizes. I think these ones looks like 0603 or 0402. It's kind of hard to see, but basically those small components these are the capacitors and also the resistors on top there, the black one. So imagine these are the sizes of the normal resistors you guys mostly work with. Those ones are like much, much smaller, so that we're able to fit a lot more stuff onto a PCB board. And we also have the pad or like footprint. Basically, that's the component, that's the area left there for you to solder the SMD components on. Let's give you a look at like a little bit more, I guess, more straightforward or like a more simpler design of the PCB, which I think is probably most of you guys hopefully gonna go through if you do decide to go with PCBs, where in this case, you don't have to worry too much about the layout. The traces can just go with, because there are a lot of space left there, but give you like an idea of which is which. So basically, the green part, the most eye-catching part, is actually a soldering mask. So basically that, usually people put it there for protection of sometimes they put it for protection of the traces underneath. Sometimes they layer over that onto the traces as well, so that if the surface got, scrabbled or such stuff, the traces still had like one layer of additional protections. This green color, I think, is the most common one, especially for the past years. Nowadays, a lot of people do like matte black. All my boards are matte black because I think that's what Apple started. So if you ever tear down your Mac or iPhone, all their boards are matte black for whatever reason. And on the bottom, so they have, I think for this one, it's a two-layer design, basically top and bottom. All the components though are on the top. On the bottom there, these these two holes are like the via hose that goes through, in this case, these two layers, so that it connects essentially here towards the back of these two traces. And give you like a little bit more complicated, this is like a 6-layer board. Usually, well, not mostly, the components still go on like top and bottom, right? But inside of these layers, there's a lot of things going on. We had, like we said, we could have like a power or ground plane inside of these layers, or just have like some, if you want to make sure the signals are properly separated, you could have, say, one layer only for the analog signals, one layer for the digital signals, etc. Yeah, a lot of design variations or design considerations could go into the board design if you do want to go like much more compact for whatever reason. But I think for most of the class, probably 2 layers should be sufficient enough. So what's the actual PCB board manufacturing steps? Basically, first we have the manufacturing file generated, which we will talk a little bit later on what are they. Basically, the name is called Gerber files. It contains the drill files, basically what are the holes to drill, also the layout files on each of the layers, telling you what are the trace shape look like on each of the layers, and assembly file in case you want to do like a machine pick and place assembly to get the components onto the board. So first we have the files for the manufacturing, and later on we have the raw materials prepared. Usually in industry they have this, they call it FR4 laminated copper thing on 2 sides. This is what it gets started on, and then this is like the default, I think, for a lot of the PCB manufacturers nowadays, if you don't have any special requirement. And then those, like the drill files that I mentioned, is actually the first to get completed. So basically the machine will drill these through holes onto the raw materials. And then later on, in order to have like electrically connection to different layers of these PCBs, because the copper was originally only on top and bottom layers, right? They will also fill some metals, or like in this case, most cases, the coppers onto these drilled holes, so that they are also internally connected. Later on, there will be like a photoresist layer, UV sensor layer being applied to the entire board, so that the part that the circuit should be naked, it was left out there, and then they give like a electrical chemical process to put like some things onto the copper. This is to serve as a protection layer for the later chemical etching. So once that's been done, it's ready to the next big process, which is the PCB etching. They have different ways to do this. I think chemical etching was one of the most common ways. So basically, the photo resistance part was chemically removed, and then the whole board was put into a lot of times basically electric etching process. So wherever all the parts that doesn't have the thin layers protections will be dissolved. Basically, you're left with a bare board with only the traces you want on this board. And then we put on like a layer of liquid soldering masks, which is what we mentioned before. Usually green, but Apple decided to do something fancier. After that, there is also some post-processing. First, what most people do, they put like a silk screen on top of it so that you actually know what are each of these components are with like a label of reference number you have in your previous design. Like usually all the resistors are referenced as R something with a number. All the capacitors are labeled as C something, and all the other components, or like IC chips are referred as U something, etc. And then we have the last part is basically the PCB surface finish. So sometimes it gives like additional layer on top of all these naked footprints or naked pads for it to be easier soldered with the components. Usually people use tin for that, but also if you want to go fancier, there's also like gold plate, etc. to just enhance the performance. So yeah, gold is not just for appearance; it's actually heavily used in a lot of the industrial applications. So there are different ways. So this is basically, this board is finished, and because we have usually larger patches of ordering, you can have them like the same board essentially inside of one panel to be manufactured, and then they can be coming out as like a panel thing. You can just easily break them out, or you can also have like user breakout panels to break out yourself, etc. Or some of the boards take advantage of these. They have part of the board being designed as those breakout board component or part for users to choose which configuration to use or which type of actual parts to connect it to, for example. And just a little bit more on the vias and the clearance, like the routing in a bit. So the via hose basically was left there for, it was drilled at the very beginning, and it was left there for connecting inner layers. Another thing that people usually commonly have to consider it is what's the space between the traces and how far away from each of the components, etc. These are usually specified in the data sheet of the components. So it will tell you what are the wires that are like more critical, which ones are more sensitive to noise, for example, etc. And which ones are like higher speed, so you should do something special about it. So that's the manufacturing process of the PCB. How do we actually design a PCB? There are generally like these 4 steps. First, you create like a schematic file. The schematic, basically like a circuit connection representations of how each of the components, like I guess first, what are the components you have on your circuit? And second, how are they connected? And then second, you will move to parts placement. Basically, you are given, this part is usually called board file. It's a file with the dimension requirement of your end PCB board, and then you will basically decide, and you will have all the dimensions of the actual components that you want to put on top of it. And then this step is for you to place the parts on it. The third step was routing. Basically, you connect all these wires as you have designed them with your schematic, and then the fourth, which is generate the files for manufacturing. Yeah, I realized that we're doing a little bit reversing, but I figured the previous part had more figures, so I put it in the front to get you guys more attention. Anyway, so the step 1, basically, it's something like a circuit diagram that you draw in your previous classes if you took any of the circuits class before. And usually they are represented underneath as like a JSON type of files that basically tells which component it is, which pin of this components connect to what. And if you want to take a peek, basically, this is how a typical schematic files will look like. You will notice that if you have, say, I think this does not have like a lot of the IC components on it, but if you do have like a, say, microcontroller or IC components on top of it, it could just be represented as a block with however amount of pins on it. You don't have to be exactly mapped with how physically it was on the chip itself. It can just be wires with labels on it, and you can use that to connect with other components in your schematics. Yeah, the reason to have a schematic is it's so that well, for a few reasons. First, it's like machine readable. The program will be able to read it, which we'll talk a little bit later part of this class. The design tools or design tools you usually use what they call EDA, electronic automation design tools. That it has to be readable by those programs, and then it's easier to find and fix bugs when compared to if you're trying to look at the PCB layouts and figure out which wires are connected to which. So next part, we will basically move to the placing component parts. And usually you just place them, make sure they fit on either the top layer or top and bottom layers together if you do decide to use both layers for the placement. Some people consider it as like an art form, how you place them. If you do work with like some very, very compact space, for example, not sure if you guys looked at the PCB board of a MacBook or an iPhone. If you open it up, like the whole PCB of this entire phone is essentially just this little. All the rest are just batteries. So for those type of, it's definitely need a lot of work. For the parts you guys design, I think it should probably be okay, and most of the signals you work with will be digital signals, so hopefully that will not be too much of an issue. Some of the tools which we will mention later do some like auto placement for you to a certain extent. It usually finishes about like 92 to 95% complete, depends on how many spaces you give it. But like generally speaking, you usually place the largest components first, and then one size smaller, and then trying to, that's like the usual rules people do this. Yeah, so once you have those components needed, let's actually go to the next one. Once you have all those components placed, you will need to wire them all together in order to have a PCB board in the end. So there are actually a few things to consider here. Usually, like the minimum trace width are specified by either datasheet or your manufacturers. So the thinner width are achievable if you willing to pay more money, but it's just something to look out for. And the minimum space between each of the traces and holes, these are usually, again, decided on either the manufacturers or your device specifications, like device data sheets. If some of the components have to at least have a reasonable amount of space between other noisy components, for example. And yeah, make sure you know which manufacturers you're going with. I think nowadays they are pretty good at using this similar standards, but just to make sure. Sometimes it's almost worse to pick the manufacturers before or know the manufacturers you usually work with, and then use that as the guidance of what's the trace dimension width you're trying to use. And we go. So some of the terminologies again, so they are usually called, they usually use the measurement unit called either by inch or millimeter because of, United States decided to use inch system rather than the rest of the world, which makes everything super complicated. But anyway, a thou is usually called a thousandth of an inch, or people, I think, mostly commonly refer it just to as mil. But sometimes that's a little bit confusing with mm, which is millimeter. So if you want to be absolutely correct, you can choose to just call it thou, basically. And some of the intuitions on what's the sizes to use. So generally speaking, they have like most manufacturers have like 6 to 10 mil as their minimum manufacturer width, unless you want to, of course, pay more. For your designs, usually you can just go with whatever the default is in your tool, the PCB Design tool, and that should generally work. And for the power and ground, usually we have like wider wires. A lot of these are the intuitions people had based on their practice. But basically for the power and ground, usually use 50 or 25, etc. And to give you like a idea of what people use for like higher powered components. For example, like a 10 centimeter trace needs to be like 10 mil wide if it carries like 1 amp. 1 amp is a lot of current to go through on a PCB board, unless it's like high power components. For like the embedded systems, 1 amp is a pretty high power consumption. If we do like a 5 amps, it's going to be at least 110 mils. So those things don't just grow linearly. It's kind of because a lot of the considerations have to go into this. Obviously, first is the heat dispense, and then the heat generated on the trace was I to the square. So it's actually polynomial rather than a linear relationship here. So after that, we have the routing. So there are two parts of the routing. First is you can call this different names. They sometimes call this a rat's nest. I usually call this air wires. So basically, this is the PCB board layout you have in terms of dimensions. And then all the components, you already put it there. This is like after the components placement. And all the pins that's supposed to connect to each other are represented inside at this stage with like a thin direct wires in between. Usually in most of the tools I know, I don't know any tools that doesn't do that actually. Most of the tools I know, they basically generate these type of air wires for you as long as you have a readable schematic files in their format. So yeah, good thing is it's good to have like a well-built schematic files. And then you will, based on this, and then draw it for real with the actual how you wanted them to go through each component, or does it go underneath, or which layer it goes through. So they are again just like previously, like the auto placement function. There are also the outer router function for your routing. A lot of times those two functions actually work at the same time, but basically this is also sometimes being taken care of. So if you have a lot of space, usually the programs nowadays can do a pretty decent job. But if you are, if you're a true professional, you will probably be very reluctant on relying on the outer router. You might use it as like a starting point, but chances are you're going to have to redo a lot of the work. I think it's hard to give like a detailed list on what's our good routing or what are bad, but generally speaking, you want them to be short. You want, for example, these on the left is a pretty good example. On the right is not so much because take much longer traces, more space, as well as unnecessarily through holes placed on the site. Some other routing things you might want to consider if you're dealing with super high-speed signals. If they're like parallels, make sure they have roughly the same length and then go along with each other, etc. Later on, it's basically generate files. These parts are again largely taken care of for you, so you don't have to worry too much. Usually, it's a few clicks away. You do have to decide what you want to put on the silk screen, or do you want to put on the soldering mask, what the text are. But other than that, it's usually been taken care of you. And the file is basically in Gerber format. It's usually in ASCII format, and these are basically machine code that's used, that was being taken by the PCB manufacturers to know where to draw, where to etch, etc. Yeah, usually you just send them as a zip file and then all together to manufacturers, and they will figure it out from there. Just give you some ideas of more complicated design. So essentially this is a schematic file, and then it goes on to this component placement, and then after that, we have the routing done. So it looks pretty complicated because they are pretty complicated, but it's a form of art, apparently. Yeah, so this is, again, a Renaissance from before. These are usually much more complicated boards compared to whatever you guys are gonna build, hopefully. I think that one at least have 6 layers there. So now that we know what's the general workflow, what are the tools to use specifically? I'll just give you a few examples here. I think it's good to mention. I pick a few commonly used tools here. Usually I categorize them as open sourced and non-open sourced. They are all fall under the category of EDA tools, electronic design automation tools. Usually speaking, non-open source ones cost you money, but they also have I guess better technical support, more package to choose from, etc. The open sourced ones usually have less of that, but some of them are doing actually pretty decent nowadays. For example, the KitKat. Some no open sourced ones are pretty. Let's give you a quick review of these. The first is the non-open source ones. It's called Eagle. It used to call Eagle. It got acquired by Autodesk. Now it's called Fusion 360. So it used to be open sourced, but not anymore. The good thing about this Eagle format is, I'm not sure if you guys look into some electronic websites yet. For example, SparkFun. Those websites with all those electronics, they actually provide you with the PCB design files, including schematic files as well as the board file. Those are usually in Eagle format. You can import it into Fusion 360 or other EDA tools. The PCB design tools that supports this format, and look at what's internally connected or how that sensor module actually works. This is how it looks like. They're all gonna look pretty similar, but just give you an idea. They have some form of 3D viewing opportunities to give you how a finished product gonna look like, and of course have some labeling on top of it if you are doing a very good design file. So this is on the left essentially a board file, and this I believe is a IMU sensor from SparkFun, if I'm not mistaken. Yes, it's a 9-axis IMU file from the SparkFun. The Altium Designer, a lot of you guys I think are using this. I think UMich provide free access to Altium Designer. This is actually one of the pretty good tools, very professional. Also have 3D views. I think it allows you to move things around a little bit in the 3D views, just for show. I don't know, but it's able to import Eagle files into this. So if you feel like Fusion 360 is not as great anymore, feel free to use Altium Standards. Yeah, this is how their UI looks like. Dark theme, very professional, nothing to pick, nothing wrong with it. So, and some UI interfaces here. There's also a thing called like an Altiboard. Actually, I never personally used this one, but I assume this is pretty similar to the rest. And if you are interested, feel free to check out this YouTube link. I'll post the slides on top of in the slides. So this is how the interface looks like. Pretty standard. Yeah. Another cool things to mention, I think a lot of people nowadays are moving towards this, is called Easy EDA. It's a online platform, web-based. They collaborate, directly partner with, or they already been acquired, actually, I don't know, but with like JLC PCB, which is a pretty big and decent PCB manufacturer based in Shenzhen, China. And yeah, they are getting better and better every year. It's pretty decent. If you are designing some like quick 2 layers PCBs or like a shield that go on top of our current STM microcontroller board, this might be the place to go. It's have like a pretty friendly interface, and then whatever you design there, it can be directly sent to this PCB manufacturer, and then they will kind of know what to do with it. And I was told that they have a pretty impressive inventory for their electronic components as well, which is quite nice because a lot of times the PCB assembly, if you want to do the assembly by the manufacturer, they require you to provide all the links and sometimes ask you to ship in your own components if that component is a little bit hard to find. So this is what the UI looks like. This is where their website, pretty straightforward. Feel free to check it out. Another good thing to do is to think about is like KitKat. I think someone called this KiCad. I'm actually not sure what's the right way, but I have always been called it KitKat since the beginning of the day. So it's open sourced. It used to be pretty crappy, but it improved dramatically in the past few years. I think nowadays people can comfortably do like a 4-layer design with this tool. Open source meaning, well, it's not going to be as well maintained, but that also give you more control of which type of or customized package you want to import into your design. So say if you build your own IC chips, and with a very weird footprint layout, this might be easier to input. And it supports some of the scripting, I think Python. So if you want to do some, say if you want to write your own auto placement algorithm, this is the one to go. Yeah, pretty decent in recent years. So this is, again, in case you want to take a look at, this is like this is their website, and then they have like all bunch of informations there to check it out. Pretty decent. Another web-based, I don't think I would call this necessarily a PCB tool. It's called Freezing. It's like a breadboard / PCB prototyping tools. Basically, this is what it essentially looks like. This is a Raspberry Pi, in case you're wondering. Basically, they give you exactly how each of these components is going to look like. And then you are able to, in real time, connect these on a breadboard design or a different type of design, depends on your choice. But I think most people use breadboard. And then this tool is going to basically simulate the whole components, how it works for you. Imagine like the other simulation tool we usually use in class, where it's like a schematic level tools, right? This is more like I guess, board level tools for that. You can just choose the microcontrollers you want to use, and then whatever components you want to use for your circuit, and then connect them together. That will give you give you an idea of how it works. This tool, I believe, supports to to output into a schematic files. So if you somehow have like a pretty satisfied circuit design here, you can export that and then work on that to move on to a PCB board after. So any questions on the PCB design or manufacturing so far? Okay, perfect. So what are the other ways to say, building PCBs, or not exactly PCB, to put like circuits onto, a substrate or onto whatever things you want to work with for your project or for your prototypes? They do have other ways that takes like less time, but have some other trade-off points. But let me just give you a few examples of what you could do as like an alternative to the PCB. First is inkjet printing. So actually, nowadays, this is like just a very off-the-shelf inkjet printers. You could essentially switch the the cartridge inside into specific silver inks and then print out a circuit. Give you like a quick examples. So obviously, these are pretty big components. We wouldn't necessarily call this like a PCB, no way. But it is able to print out something like quite finite. That's essentially a board design for a Arduino board. You can print out the whole thing with the inkjet printer. How it actually works is basically it's essentially like 2D inkjet printing, right? You basically design however your circuitry looks like in any of the drawing files, for example, Adobe Illustrator or other 3D design tools, as long as in the end you output like a PDF file. And then we use the silver ink and paper sheet we use the silver ink to replace whatever the color cartridge inside of a commercial inkjet printers. And then we basically print out just as if you were printing out a PDFs. The paper sheets usually are pretty specially made. They have some chemical coatings on top of it. That's how the silver ink got reaction with the top of the sheet and then get the trace bonding together well. Give you like a quick, I think if we go, yeah. So basically, it prints out fairly well. Very fast. Like usually just like a few minutes compared to if you do like a say 1 week turnaround time with the file. So obviously there are some, like as we usually says, there will be some drawbacks on these. To start with, it's usually much harder to connect the components or put your SMD components onto these inkjet printed circuits. They have been different ways and different researchers exploring on this. One of my previous work was around these topics. They have been works with using Z-tape, basically the electrical conductive tape that goes only through Z directions to essentially stick your electronic components onto the circuits. But at the end of the day, it's not gonna be as rigid. Obviously, it's not gonna be as robust as a board compared to like a PCB board. But the hot catch here is it's super fast. So it would be pretty good to use for example, you want to connect some boards together. Rather than go through like a whole PCB design, you could get something flexible with reasonable amount of connections instantly almost. Basically, if you don't have any physical components that has to go onto this area, this is like the perfect, it's a very good fabrication method for your circuit. If you do, then you have to be a little bit more cautious on how you connect these components onto your circuits. There are also other ways. You'll be surprised. There are also people drawing their own circuits. So instead of drawing your own schematic, you can also directly draw your circuits. There are a lot of these silver pens outside that people used to use these to do like some quick PCB PCB fixing. So if you have like one of the trays being down, or if you want to bridge two of the pads. Wow, that's very loud. Okay, if you want to bridge like two of the pads on your PCB, these are what people used to do. Basically, place some like silver pens or like silver inks essentially, and then later on, some folks figure out you can actually just directly draw the entire circuit on it, and that will work pretty reasonably. Obviously, not recommended for whatever final project you're doing right now, because I think a lot of them have like moving parts, so that might make the whole thing be like, oops. Does it play? Yeah. So this is like a purely drawn component, and then it controls some of those electronics connected to it. You are able to do like multi-layers on this. Believe it or not, it's actually just you put some layers in between, and then layer like a isolation layers, and then put another layer and draw on top of that. We also have these vinyl cutting methods. So not sure if you guys work with these. Essentially, if you remember from the PCB manufacturing, it's essentially one piece of big copper that's being etched away of whatever you don't want, right? Similar things can be done with like other type of one piece copper. Basically, we cut out whatever the part doesn't need and leave with whatever the traces you want. The end product, it's pretty similar to the inkjet printing or to like copper traces, but it's a little bit thinner. It's usually done through like copper tapes on, they have those like super white copper tapes with a thin layer of copper on top. And this is like one of the stuff you can do. This is like a Stanford bunny. I'm not sure if you guys know much about this, but basically you are also able to do like multi-layers by just doing like an isolation layer on top of this, and then you can have like multiple layers of traces. Just like before, they have the drawbacks on which type of like how you're actually going to connect this to the rest of your circuit. Again, if it's only the circuit that you're looking for, these methods are pretty decent. If you do want to have components attached to it, it requires a little bit more thinking. This is the Stanford bunny in action. Yeah, it gives you like a representation of where the thing was touched. We also have other different methods, like using conductive yarns to basically stitching the circuits together. So on the left here, I think this is called, it's also one of the family under the Arduino. Some of the researchers at MIT Media Lab, they decided to build like a toolkit thing for wearable electronics for clothing specifically. So what they do is, I think it's called Arduino pad, something. So basically, instead of like the normal during line components that you stick into your breadboard, they basically have a bunch of these surrounding pin-out that's very easy to be stitched or wired with yarns onto the clothes. So these are also a lot of these are used for like artistic projects, for like those fashion shows before, so that you can have some electronic circuitries essentially embedded into soft fabrics. We also have like screen printing. I think this is much more traditional. I think a lot of the industry sometimes also use these. This is like a method they use for like when you do the soldering, when you're doing soldering a large bunch of stuff, you use this to display the solder paste onto each of the naked pad with a mask on top of it. So similar method can also be applied to your circuitry design. Essentially, you use different materials. Instead of using solder paste, you use silver paste, and then have like a laser cut it or some type of masks onto whatever you want the circuit to happen, and then brush it over, and then let it cure, and then you have the circuits left on the substrate. Of course, we have the spraying. You can also directly spray on, again, with the masks. It's very similar ideas, but using different type of fabrication techniques. Basically, you print it out, the circuit you want with the mask, and then you have the circuitry left on whatever surface you want, and then you're able to add in more stuff on top of it. Pretty fun project. You can directly just touch it and then turn it off or on, in case you want to put some circuit on the wall for whatever reason, or onto sofa. So one of the good things about this is the spray painting method is that it's pretty good for various different surface. For example, if you have like a more stretched surface, doubly curved, like a rigid PCB would not fit well, then these are some good methods to think about. You can basically spray painting the entire circuit onto that component. And of course, we have the 3D printing with conductive filament. It's, I would say, still under developing for like a very good filament that has both very low resistance and also very, very 3D printable. So I think for this one, usually people are still stuck in like applications like capacitive sensing rather than print out like a proper PCB board. I think we're still a little bit away from that, but just give you some ideas of how it works. We have like conductive filaments. Usually it's some form of either plastic PLA or ABS or TPU, those like flexible materials mixed with some like carbon or carbon particles or carbon fibers, etc. That gives it give the filament conductivity. And some of the prints that people have done, something like a joystick controller or like some sad-looking robot that it's. Like I said, they do have now filaments, I think Electrify, that's the name. They claim to be superconductive and almost circuit level, which is true, but they're also very hard to work with. Like it's pretty hard to print them out in a good manner, and then it would be just like any of the traces of your PCB. So there's still some research needs to be done around this, but just be aware that this is also a type of fabrication, like type of alternatives to your PCB manufacturing. So if you want some trace that's like short in length, so these wires are still totally doable. And if you don't care about power consumption, of course. There are also some people who just decide to 3D print out the whole thing in the shape of how they will look like in a breadboard or components. It's fun to look, but it's basically how. Yeah, these are again just like some conductive capacitive touching components, but in the shape of a breadboard. They are also very interestingly. They also did, obviously there are a lot of people working on this right now, but they also have like a proper PCB board underneath that basically take whatever they input on top and then simulate how that component should behave in the real world. For example, if it prints out like a buzz or like a buzz, like when you touch it, the system underneath, like the PCB board underneath, will know someone touched it, and then it makes the buzz throughout that PCB board through another speaker but it gives you like a understanding of how the circuit works. This, I believe, serves more like educational tools of like early stage circuit prototyping. You can think of this like the freezing, like the one I mentioned before, for you to prototype inside of the breadboard and microcontroller on a web base, but they put that into like a physical format. And of course, we're gonna have something more wacky. So you could also just 3D printing on the body or 2D print on the body. So this, essentially what they did is they have this little structure right onto your body and then have like a syringe dispenser. So you can essentially think of them as 3D print head, but with step motors that pushing out and retracting the ink inside. So I believe this one they use the silver paint as well. So basically, let me see if, yeah, motors and inks, and then whenever you have you want to do, usually you put down like a protection layer so you don't poison yourself, just to be safe. And then you do, again, similar to the previous design tools, you have like the drawing of whatever you want to print in like a 2D format. This, you think like, you see a lot of these work are pretty much adapted from the PCB manufacturing process. You know, once you have those 2D layers, how the wires are connected, etc., and then you take those files but fabricate them in a different format, essentially. And then once you have those things, you basically just go through and then push out the ink. Looks pretty cool, right? So yeah, of course you have to let it cure a little bit. Sometimes it, you know, might be a little bit more. But anyway, these are like different ways to do this. And if you are interested in how various ways to do this, these type of things, feel free to take my class next semester. It's called How to Almost Make Anything Interactive. So that's the end of today's lecture. If you have any questions, feel free to come down to me, and then we will chat it out. Thank you.
We like some stuff, but none of it came yet. We don't have any of like
Oh, wasn't created yet. As long as you guys I know. Actually, you have to. I know a lot of the things. I thought I knew like most of It was like if you have a high bandwidth thing, SPI more parallel. Last one again. Oh, don't you remember when like all those what is? What is high bandwidth? I didn't put SPI. I didn't put
We pre-made the script and all that. We pre-made the script and the organization for that.